This is a production of Cornell University.
All right, thank you, Harold, and thank you everyone for being here. Based on the presence, I'm assuming we have some coffee lovers or soil health lovers or both or neither, which is fine. You're probably here because you're taking a class and you need to be here, but I'm hoping that it'll be an insightful presentation. So to give you some background information about coffee production in Colombia, almost all of our coffee that we consume is produced by smallholder farmers in Colombia. And it's been increasingly challenging for them to keep up with production and earn a consistent income because of the price fluctuations, the market price fluctuations. As you can see from the 1970 to 2016, you see drastic changes, which makes an inconsistent income for farmers. The other issue is drastic changes in climate trends. This was an article in The Guardian about 2.5 months ago about how climate change is predicted to have coffee growing area that supports these smallholder farmers. So soil health actually can be a solution in a sense that it may offer coffee farmers a marketing advantage and significant price premiums by promoting sustainability. The FTP here, which is the Fair Trade Proof, is just one example of an organization that provides price premiums based on social, economic, and environmental sustainability. And sometimes these price premiums can be so high to be double what your regular commodity price is. So the purpose of this multidisciplinary study, let me turn this on. So the purpose of this multidisciplinary study is to identify the characteristics of soil health in Colombian coffee systems to better address the issues of economic, social, and environmental sustainability. So the outline is, this study consists of 3 parts. The first part is a very sociological, anthropological based study that consists of understanding soil health and associated farmers' perception in Colombian coffee systems. The second part is to determine the association between coffee cup quality and soil health. And the third part is a comparative analysis of the different regional scoring frameworks. So our study was located in 6 municipalities within the Department of Cauca. Department is equivalent to state. So Cauca is located in the southwest part of Colombia. And farms in each municipality either belonged to the local coffee co-op or didn't belong. So they were members or non-member farms. From the member farms, 2 soil samples were collected. The most fertile sample as indicated by the farmer. So we went to the farmer and we told him, okay, we want you to identify in your farm the most fertile plot, and we sampled that. And, and the least fertile, and the same thing as indicated by the farmer. And then one representative sample was collected from the non-member farms. So this is great information for to assess the perception of farmers of soil health. So the samples were collected. They were sent to the soil health lab here, and a number of physical, chemical, and biological indicators were measured. Physical indicators included wet aggregate stability, which is measured using a rainfall simulator, which delivers 12.5 millimeters of in 5 minutes, and available water capacity, which is measured using pressure chambers that extract water at 2 different pressures, the 10 kilopascal and the 15 kilopascal. Biological indicators included organic matter, which is measured based on loss in ignition, active carbon, which is measured with potassium permanganate oxidation and measured with a 550 nanometer spectrophotometer. Soil respiration, measured by capturing CO2 in a 4-day incubation using potassium hydroxide. And the soil protein index, which is extracted with a citrate buffer under high temperature and pressure. Finally, the chemical indicators included pH measured in a 1-to-1 water slurry, phosphorus, potassium, and the micronutrients were all extracted with modified Morgan and quantified with the ICP. So the soil health scoring was undertaken using a cumulative normal distribution. So the cumulative normal distribution is the derivative of the Gaussian distribution, the Gaussian distribution function, and it gives you the probability that a member of the distribution is less or equal to your measured soil health indicator. For instance, if we look at active carbon, if we look at the measurement 600, and you derive the distribution, it gives you, 600 would be here, it gives you that the score would be 50%. So in some way you can look at it as a ranking scheme. So the parameters for mu and sigma, which is the population mean and the population standard deviation, were either estimated from local conditions, and this was done where thresholds and critical values for specific soil health indicators have not been established. So in the literature, it's nearly impossible to find the thresholds or the optimum levels for available water capacity, organic matter, active carbon, protein, respiration, and phosphorus. So in that case, you estimate the population mean and the standard deviation using the sample mean and the standard deviation, the sample being the n equals 223. For parameters, the parameters were also determined from existing critical values found in the literature specific to coffee soils, and hence was the case for potassium, magnesium, zinc, manganese, and iron. Wet aggregate stability was the exception. Wet aggregate stability, when you plot the distribution, it's very left skewed in that all of the measurements were on the high end. They were 90. And so we used the measured values as the scores themselves because the measured values is a percent-based measurement. So we use those are scores. And then overall soil health is computed as the unweighted arithmetic mean of individual soil health indicators, meaning that you calculate the scores for each individual, for all of the indicators, and then you take the mean and you get your overall soil health score. So these are what the soil health scoring curves look like for each indicator. There are two things to note in this graph. So some scoring curves follow a more is better curve, which is the case for the following. And then some of them followed an optimum range curve, which was the case for pH, iron, and zinc. And then some of them followed a less is better, which is manganese. So the less manganese you have, the higher score your soil has. The other thing to note about this graph is that some indicators required accounting for texture. So we adjusted them for texture. And those were the indicators that showed significant difference in measured values between the different textural classes. And so this was AWC, organic matter, active carbon, and respiration. We did not develop curves for coarse textured soils because we did not have a representative sample of coarse textured soils coming from Colombia. So the first part of the multidisciplinary study is understanding soil health and associated farmers' perceptions. And the objectives were to determine the geodemographic and environmental factors that play a role in farmers' perception of soil health and its accuracy, whether coffee farmers have accurate perceptions of soil health, and the soil health indicators most associated with farmers' perception. The statistical analyses used here were ANOVA for factors influencing soil health and farmer soil health perception accuracy, a Fisher's exact test for count data, which is a more accurate test than chi-square and the g-test when your sample size is less than 1,000. And we use that for the factors influencing farmers' soil health perception accuracy. And then we also did a logistic regression and a principal component analysis for the soil health indicators most affecting farmers' perceptions. So in these box plots, we have soil health score on the y-axis and and the gender, municipality, and membership variables. So our results actually show that female farmers have significantly higher soil health than male farmers. Yes, they have, and someone needs to tell this to Trump. I think that would be that would be interesting to see what his reaction would be. So furthermore, we saw significant difference among municipalities in terms of soil health. Rosas having the lowest mean and Cajibillo having the highest mean. We also found that members have significantly higher soil health than non-member for co-ops, which makes sense. That means that the services provided by the co-op have measurable positive impact on the soil health. Our results also show that coffee farmers have correct perceptions of their soil health. So on the y-axis, again, we have the soil health score, the measured soil health score from the lab, and these are the perceived soil health. So this is what they ranked most fertile and least fertile. And on average, we did find that the most fertile, what they specified to be most fertile, was significantly higher than the least fertile. Finally, when we were interested in seeing what factors influences farmers' perception of soil health, when we looked at gender, we saw that there is no significant difference in terms of their perception accuracy. Their ability to perceive their soil accurately did not differ between gender. It did not also differ between municipalities. But we saw that it did differ based on the actual soil health, meaning that farmers who had higher soil health were better at predicting their soil health. And you see this by this linear, significant linear model. So a principal component analysis is a great way to visualize patterns and really describe your data. It's really important for two reasons. It helps you detect variables and attributes that are that have high impact, but it also helps. It's really useful for dimension reduction. So if you want to achieve a parsimonious model, then PCA would be a great way to do that. And so that's what we did. We used PCA for the logistic regressions, which I'll show next, to assess which indicators affect farmers' perception, farmers' perception of soil health. So in the first principal component, which explains 34% of the total variability, you can see that it's very biological heavy. So most of the indicators are biological, and we do have some physical. And then the second principal component analysis explains 17% of the variability and is very chemical based. So for the sake of having a parsimonious model, we used the values the values with strong correlation. So those are the ones in bold. So our logistic regression showed that organic matter, protein, and respirations are indicators that are most related to soil health perception. Organic matter had a significant positive relationship with farmers' perception, and this makes sense. You see it in the literature. Organic matter is a very effective way of assessing your soil health when measured data are lacking. Protein also had a significant positive relationship with soil health perception. The only way I can explain this is protein is basically the nitrogen-bound organic compounds, and somehow the farmers have a perception of the importance of nitrogen and the availability of nitrogen, and that somehow translate into being able to perceive their soil health. What's interesting is that respiration is also significant, but it's negative. And the only way I was able to interpret this is that the farmers seem to are confused between beneficial biological activity and detrimental pest infestation, which throws off their perception accuracy. That's the only way I was able to interpret this, and I'm happy to hear your input at the end of the seminar. So the second part of the study was to assess whether soil health has an effect on coffee cup quality. So to assess the existence and the existence and the nature of the relationship between coffee cup quality and soil health, and the soil health indicators that are main predictors of coffee sensorial attributes. We selected 68 member farms that were demarcated by 20 by 50 meter quadrants. And then we did an inventory for tree density, which is a proxy for shade coverage, which literature has shown to have a positive impact on cup quality, and also elevation of the farm. Coffee cherries were also sampled, and the statistical analyses used were the correlation matrix and linear regressions to assess the relationship between coffee quality and soil health, and a best subset regression for coffee sensorial attributes to soil health indicators. So this is an example of a coffee report. So coffee is assessed by a professional certified cupper that assesses a number of physical, sensorial attributes, and also granulometric, which is a series of sieving tests. This is the list of all of the sensorial attributes and the physical attributes. So all of the individual scores are composited, and you have a total coffee score. So the correlation coefficient of coffee quality scores with soil health indicators show that available water capacity and organic matter are significantly negatively correlated with coffee cup quality. You also see a negative correlation with phosphorus and iron, but a positive with manganese. When we run a linear regression, we first used a full linear model with all of the soil health indicators, the number of trees, and the elevation. And our model did not come out to be significant at all, and we had a negative, which indicates that it's a very poor linear model. So what we did was we did a best subset regression of the 5 best predictors, which are in bold, and so we extracted these and ran their separate linear model. And that's when you start to see significance. So again, you see a negative correlation with organic matter. The estimates are negative. Protein, respiration has a positive estimate, and then pH and iron have a negative. So these findings are puzzling. You would think that, you know, higher soil health is better in every dimension. But after much thought, we think that coffee might actually be very similar to grapevines, in that you don't necessarily want high soil health, and that additional organic matter or water holding capacity or pH doesn't necessarily translate to better coffee quality. And so you see again this trade-off between quantity and quality, where this farmer has to decide whether to maximize yields or achieve premium coffee quality. And in terms of the micronutrients that we see here, I looked at the literature and I still can't know how to translate that don't know how that translates into coffee cup quality. So a best subset regression was used for predicting coffee sensorial traits. So you see all of the sensorial traits here and all of the soil health indicators here. And we noticed that iron, phosphorus, and wet aggregate stability were consistent in predicting coffee sensorial traits. They were the best 3 predictors of coffee sensorial traits with a fairly good R-squared value. And so this is important because it could provide an alternative to the different sensorial assessments. The third and last part of the study involved a comparison of the regional soil health scoring frameworks. So we did this in an attempt to assess the feasibility of developing global soil health standards, which is sort of aligns with the NRCS goals of achieving national soil health standards. And so the objectives were to assess whether different regional scoring frameworks yield similar results, and to develop a simplified version of the Colombian coffee soil health scoring framework. For this, the 223 samples were subjected to 3 types of indicator and overall soil health scoring. The scores were compared using a t-test and an inter-rater reliability test, which gives you the ICC and an interclass correlation coefficient, which gives you the level of agreement between the different ranking mechanisms. So if you have an ICC of 0.2 or below, you have poor agreement between the different scoring mechanisms, and above 0.8 is in an almost perfect agreement. So currently there exists 3 regional scoring curves that we know of. The comprehensive assessment of soil health, that's the scoring framework developed at Cornell, specific to the Northeast. The Colombian coffee soil health scoring, specific to Cauca, Colombia. And the Western Kenya soil health scoring functions, which were developed by Bianca, some of you know Bianca, and colleagues. So these are what the different scoring functions look like. These are categorized by the textural classes, so fine texture soil, medium texture soil, and coarse texture soil, and these are for the different regions. Again, a CND is the cumulative normal distribution, which is the derivative of the Gaussian distribution. And when you compare, if we take, for instance, if we look at wet aggregate stability, again, we used the measured values to score the wet aggregate stability in the Cauca Colombia framework. But if you compare Western Kenya and the Northeast, you see some differences in terms of the scoring function, which is composed of the mean and the standard deviation. So you see 58 and 43, 19 and 17. So there is about a 15% difference between means. And if you go across the different scoring textures, you could also see that in medium they're closer, they're fairly close. And the same thing for available water capacity. You see, so in this case, in medium texture soils, the mean for Western Kenya and the Northeast are identical, and the standard deviations are very similar. So these are just the different scoring functions by textural class and by region. So additionally, we also performed a methodological, developed a methodological framework which we named the weighted Colombian coffee soil health scoring. And the overall soil health was computed in this framework as a weighted mean of the individual soil indicator scores plus texture. So if you remember, the approach that we used previously was as an unweighted. It's just a mean, a regular mean. But this was weighted. And the weights were determined using a PCA, where the sum of the eigenvectors of the first 4 principal components were the actual weights. And so you can see here that biological indicator seems to have the highest weight. I know this will make Janice really happy. So the formula for the weighted overall soil health is basically the soil health indicator times its weight, so on, over the sum of the weights. And these are the results. So there are 2 things to note in this slide. So the t-test shows that the different scoring mechanisms yield significantly different scores. However, in some cases, the ICC, the intercorrelation coefficient, was high, which indicates that there is actually a strong agreement between the different scoring mechanisms. And this was the case for wet aggregate stability, protein, and the overall soil health scoring. In other cases, the results from the t-test matched the results from the intercorrelation coefficients, meaning that the different scoring mechanisms yield significantly different scores, and so that the different scoring mechanisms are different. And this was the case for organic matter, respiration, pH, and phosphorus. So the way to interpret this discrepancy between ICC and the t-test, between the intercorrelation coefficient and the t-test, is that although sometimes the t-test indicates that they are significantly different, in reality they're not, because the different scoring mechanisms seem to generate scores that are in the same range, meaning that 99 and 94 and 96, they're all high. It doesn't, maybe the means are significantly different, but the three scoring mechanisms consistently score the soils high. And it's the same thing for the overall soil health. They're consistently medium. But in other cases, they were significantly different. So lastly, given the financial, the logistical, and the resource constraints of smallholder farmers in Colombia, we tried to develop a simplified and less expensive version of soil health assessment. And we used this using a best subset regression. So the best subset regression is a type of regression that models all possible, that basically generates all possible models based on a specified number of predictors. So if you want one predictor, it'll give you the best model with one single predictor. And you could also choose a set of 2 or 3. And so when you look at the best single predictor, active carbon had very high predictive power in predicting overall soil health, followed by organic matter. And this is a great finding especially because of the nature of the active carbon assessment, which is very easy and very inexpensive. Basically, all you need is some potassium permanganate and a small field spectrophotometer, and you can have your active carbon measurement in a matter of 20 minutes, about. And then if you add other indicators for higher predictive power, that's when you see protein and respiration play a role in predicting overall soil health. So it's not until groups of 3 where you start seeing some chemical indicators as major predictors. So what have we learned from this big multidisciplinary study? We learned that female farmers and co-op members have significantly higher soil health than their counterparts. Farmers appear to have correct perception of their soil health, which is not associated with their gender or municipality, but with how healthy their soil actually is. Organic matter, respiration, and protein are indicators that are most related to farmers' perceptions of their soil health. We also learned that coffee quality is significantly higher with lower soil organic matter, water holding capacity, and pH. And iron, phosphorus, and wet aggregate stability were consistently best at predicting coffee sensorial attributes. Finally, in the last part, we learned that achieving global soil health standards is possible, especially when only considering the indicators that showed a high ICC, an intercorrelation coefficient. Oops. We also learned that active carbon is a great test that can highly predict overall soil health and can be used in a simplified version of a soil health assessment. With that, I'd like to acknowledge my source of funding, the NSF GRFP. I'd like to thank my major advisor, Harold, who's been mentoring me ever since I was a dumb undergrad and been very patient with me. Miguel Gomez, who hired me as an undergraduate research assistant my senior year and who got me involved in this project. And Dr. Hobbs, whose invaluable international work has really taken this research to a whole nother level. I also want to thank Kirsten Kurtz and Bob from the soil health team. Kirsten was the one who taught me everything about soil health and how to run all the samples. And I actually started, when I first started working in the soil health lab, I started with the Colombian samples. And Bob, who's been the behind it all, just organizing everything. And then Stephen Perry from the Cornell Statistical Consulting Unit, who's been giving me statistical advice throughout all these chapters. And then the story behind this slide is actually pretty deep. It's not just your regular thank you slide. So when I was doing the literature review for the third part about the global soil health standards, I did so much literature review that it was a pain in the neck. And I had to teach myself how to read dense academic papers in 4 different languages. So I had to learn how to read papers in Portuguese, in Spanish, and French, which thankfully I already know, and English, of course, I already know. So these are the languages that I used in my literature review. And that's all I have. Thank you.
This has been a production of Cornell University, on the web at cornell.edu.